blades are a complex aerodynamic of the bearing journals on the shaft. For good control of the rotating assembly and reliable, quiet operation, the journals need to be as close as possible to a perfect cylinder. We work in microns, which is 1/1000th of a millimeter. A typical tolerance on that cylindrical shape is just 2.5 microns. To understand these small sizes, we can compare to a human hair, a human blood cell, a particle of dust, and a tobacco smoke particle. We store and assemble these parts in very clean conditions. The new turbocharger must also be installed onto the engine with care, using only fresh, clean oil of the correct type. Oil from the engine lubrication system enters the turbo and is distributed to the journal and thrust bearings. All turbochargers use 2 oil films, one between the center housing and journal bearing, and one between the bearing and the shaft. The clearances are often mistaken as being excessive play when examining a new dry turbocharger. But this is correct and necessary for the correct functioning of the turbo. The oil flows through both the journal and thrust bearings. Oil throwers at the turbine end and compressor end then collect the oil and return it to the engine sump. Notice that the oil inlet is much smaller than the oil drain. Full details of the bearing and oil system will be explained in a later training course. The oil also has another important function: to cool the rotating parts and bearing system, preventing damage due to heat soak from the extremely hot turbine end. When the engine and turbo stop, the cooling oil flow stops and the temperature in the bearing area reaches its maximum approximately 2 or 3 minutes later. If the temperature is excessive, this can cause the residual oil in the bearing to burn and turn to hard black carbon, called coking, which will rapidly damage the turbo. The use of a shroud or heat shield controls heat soak by diverting the path of the high temperature away from the bearing system towards the turbine housing flange, reducing maximum temperature in the bearing area. This simple part is highly effective. But for higher temperature conditions or where cooling airflow is minimal, we may use water cooling connected to the engine's own cooling system. Even when the engine stops running, the thermosiphon effect of the system continues to cool the turbo. Compressor wheels have complex aerodynamic designs optimizing pressure, flow, and efficiency for each application. Ambient air enters via the inducer and exits at high speed from the exducer section of the blade. Air passages formed between the large main blades are often divided by smaller splitter blades to optimize performance for many applications. The wheel is balanced in two planes with balance cuts typically on the nose and back disc. All components are then assembled following a tightly controlled process, which includes many poka-yoke devices to help eliminate possible errors of wrong components or incorrect assembly. A red light prevents operators from passing errors forward to the next stage, and green lights indicate a correctly completed process, which then allows the next stage of assembly to continue. The last stage of the assembly process is to correctly tighten the lock nut, test for oil leakage, and then the CHRA passes into the high-speed VSR machine for a balance check. Any final balance corrections are made at this point, and then the finished CHRA is ready for assembly into a turbocharger.